Welcome back to Metrics Explained. In this new piece, we will be talking about a metric that has a monster of an acronym. We will be talking about the ROC AUC or AUC ROC or area under the ROC curve. We will be talking about the area under the receiver operating characteristic curve. What's that about? Let's find out. We already looked at sensitivity or recall in our previous video about balanced accuracy. In short, we calculate the correct predictions for each class divided by the number of samples in each class. In the following, we will simplify our problem a bit, so it's easier to understand. We now only want to decide if it's a dog or not. So we pack cats, birds, cows into a single class. So here this means we still have 10 dogs, but now we have 5 plus 3 plus 6 non-dogs. Of course, this also changes our confusion matrix. We can then calculate the sensitivities for the class dog and for the class non-dog in a similar way as before. We now consider the dogs as positive, the non-dogs as a negative class. Every dog that was correctly classified as a dog is a true positive. If it was wrongly classified as a non-dog, it's a false negative. Likewise, if we correctly classified a non-dog, it's a true negative. But if we considered a non-dog to be a dog, it's a false positive. We can then define the sensitivity with these as the true positives over the sum of the true positives and false negatives. It is thus the rate of true positives in the actual positives and therefore also referred to as the true positive rate or TPR. The sensitivity has a sibling that is sometimes a bit confusing, the specificity, also sometimes called the true negative rate. It's just the opposite of the sensitivity and defined as the true negatives over the sum of the true negatives and the false positives. So this metric uses the remaining values from the confusion matrix that we did not use before. By a simple reformulation trick, we can also express this as 1 minus the rate of false positives, commonly named false positive rate or FPR. Let us calculate this now for our example. The true negatives are 7 and the sum is 14, so we have 0.5 for the specificity. But wait, you might say, I've had this number before. Isn't that the same as the sensitivity of the negative or non-dog class? Yes, this is exactly the point. And this is sometimes confusing to my students, especially when they don't find a method to calculate the specificity in scikit-learn, but they find a method for calculating the recall or sensitivity. Specificity is nothing but the sensitivity or recall of the negative class. Let's look under the hood now. So far, we have considered for every sample the corresponding decision into dog and non-dog. And we've summed up over that to get the confusion matrix. For these 10 dogs, this is what we've had. But what really happened is that the classifier gave us a score, which we commonly refer to as the confidence for every dog that we presented to it. To see more clearly how this worked, let's sort the dogs by classifier confidence now. Much better. Now we can see how this came about. In fact, there was a decision threshold at play, apparently at around 0.5. Samples below the decision threshold were decided to be non-dogs, above were decided to be dogs. So above the threshold we got true positives and below we got some false negatives. Of course, we can lower the decision threshold and have less false negatives. All the way to 0 and we have no false negatives. On the flip side though, with the thresholding being at 0, we just detect every animal as a dog. You will see where this leads to. On one side, with a reduced detection threshold, we get more true positives and less false negatives, and a higher true positive rate or sensitivity. Cool. But on the flip side, we also get more false positives, less true negatives, and an increased false positive rate, which we want to avoid. Vice versa, if we increase the threshold, this yields less false positives, more true negatives, and a lower false positive rate, but also leads to a reduction in the true positive rate, which we also want to avoid. It thus becomes like a trading game where we trade the true positive rate for the false positive rate and vice versa. Now, depending on the application, we might be able to tolerate a higher false positive rate or a higher false negative rate. If we want to judge the quality of the classifier, however, we would love this to be independent. Let us take the true and false positive rates that we can change by varying the threshold now and put them into a joint coordinate system. We already know one point, which is at a TPR of 0.7 and an FPR of 0.5, which we calculated earlier. We also know that the threshold of 0 will give us no false negatives, but also a maximal false positive rate of 1.0. And likewise, a maximum threshold will give us no true positives. By varying the threshold and calculating the TPR and FPR, we can establish a curve. By varying this threshold, we effectively become independent of it. Moreover, since TPR and FPR are independent of how often a class occurs, we can also become independent of that. But a curve is not a metric, and we would like to have a single number. So what can we do about that? By effectively integrating over the curve, we can calculate the area under the curve. The minimum sensible value is 0.5, as this is what can be achieved by setting random values alone. This gives us a single value to judge classification performance of binary classifiers. So the area under the ROC curve is extremely useful to see which classifier performs better or worse. And it's also a metric that we used in the MyDoc challenge, link somewhere up there. Alright, that's it from my side for today. Have fun and stay above the baseline.